Newton's zeroth law, which was assumed at first but was added later as a official law, says that the object is only affected by forces acting right now. The zeroth law is the no memory and no anticipation of forces. Newton's first law talks about the effect of forces. It says that an object that is at rest will remain at rest, or an object that is moving will move in a straight line with constant speed. Both of those are fancy ways of saying that the acceleration is zero. If and only if is our biconditional term, and the net force acting on the object is zero. So there's a couple takeaways from here. You'll need to know all of these takeaways. Quoting the law is great, but there's a couple more things to know. Number one, this is defining this quantity called inertia. Inertia is the resistance of the object to acceleration. So if an object is moving, the object that is in motion will keep moving forever unless a force stops it. This is also telling us that all accelerations are caused by forces, and only forces are causing acceleration. There's also Newton's second law. Newton's second law gives us the relationship between how much force we get and how much acceleration. F equals ma is the easy way to remember it. Technically, A is F over m because the force is the cause and the acceleration is the effect of that applied force. Notice that this is the net force, the sum of all the forces acting at a given instant. So force and acceleration are going to be parallel to each other. They're going to be in the same direction. Mass is a scalar, and so that's going to scale the size of the acceleration, but it's going to be proportional to the force. Newton's third law also has a few key points that you'll need to know. Newton's third law says that every force is part of an action-reaction pair of forces. This action-reaction pair is due to the interaction between two different objects. The action-reaction pair acts on the two different objects. These forces are equal in magnitude and opposite in direction, so they are negative vectors of one another, and they are simultaneous. They come into existence and they end their existence at the exact same time. So knowing the equation is good to know. Saying every action has an equal and opposite reaction is just fine, but it's important to know these implications. A couple other points here. The mass of an object is technically the inertial mass. We talked about inertia for Newton's first law, where we said that inertia was the resistance to acceleration. The mass of the object, or inertial mass of the object, is a measurement of this concept or quantity. It depends on the material that the object's made of, and it describes the resistance to acceleration. So a more massive object will speed up more slowly from rest, but a more massive object will also slow down more slowly and will continue moving for longer than a smaller object. Mass is measured in kilograms in the SI system or in slugs in the imperial system, and one slug is about 14.5 kilograms. Limitations for Newton's laws. These laws are not valid for speeds near the speed of light, and for objects on the atomic scale, objects the size of molecules and atoms and such. Those are the purviews of relativity and quantum mechanics, respectively. Newton's laws are also difficult when you have a position-variant force, basically when you have a force that is a function of the location of the object. It's also difficult to use when you have a multi-body system, when you have multiple interacting objects. We're going to see how there are other approaches that we can use that will be able to analyze these systems without having to use Newton's laws.